Hello. Thank you everyone for coming. As you can see, we'll be talking a little bit about Flame, which if you don't know, it's the game engine for Flutter, and how to make 3D, and I say real 3D, like this green screen, real 3D, and I'll explain why the real in a bit, games. First of all, I'm introduce myself. My name is Luan. I'm the original creator of Flame a long time ago. And since then, we have come together as this Blue Fire organization, as you see. And we make the packages that you know and love, like Flame, audio players, gamepads, everything around the Flame ecosystem. So these days, it's much more community effort than anything else. And we're always happy to take contributions. So, 3D, right? And why do I say real 3D? Well, a while ago, actually, in previous Fluttercon in Berlin, I gave this other talk that I called Flame in Pseudo 3D. So that's some backstory as for this one. You can think of it as a sequel, but it can be taken independently. And mostly in that talk, I was trying to focus on this one question. Because I said, well, I get asked a lot. People ask me, does Flame support 3D? And I always had a hard time answering that question because I always said, well, this is really complicated because, you know, what does it even mean? Like, what do you mean by Flame, by support? What do you mean by 3D? So the other talk, I tried to explain a little bit more all these questions. But in this one in particular, I'm going to focus on this last one, what do you mean by 3D? Because basically the whole gist of the other talk was, even though it's not real 3D, there's just lots of techniques to make your 2D games look and feel kind of 3D. So that was the other talk. But in that talk, I did pull up, well, Flame is like built on top of Flutter, right? So in order for Flame to support 3D, Flutter has to support 3D. So I went to the Flutter website, and I went to their FAQ, and I scrolled down, and I found it over there. Can I build 3D apps with Flutter? Oh, nice. But it said, no, doesn't support it. So yeah, Flame can't support it. And hence the whole previous talk about how we can get around this. So a few days ago, I went back to the Flutter website, and I checked the FAQ again, and lo and behold, well, it wasn't updated. It still said no. So yeah, can't do 3D. Well, no, that's not true. Everything changed. Because you might have heard recently, Brandon has published this article about Flutter GPU. So if you're not aware, Flutter has this new rendering pipeline called Impeller. And Impeller gives us something new that the previous thing didn't have, which is access to the GPU. And through this new package called Flutter GPU, which is a very low-level package, it allows us to access the GPU, which allows us to do the kind of real 3D that I'll be talking about. But I think we're getting ahead of ourselves. I want to really explain what I mean by real and what exactly we're talking about here before we get into the implementation. So the first thing to understand about the real 3D is, well, what is 3D to begin with, right? So when I say 3D, and I put this, I want to get this out of the way so I don't go back to these topics anymore. But when I say 3D, I mean 3 dimensions of space. Now I know, you know, I'm a physicist, so you heard like, oh, time is also dimensional. Maybe there's 4 dimensions. Maybe there's 11 dimensions. Like, I don't care about any of that, right? Any reasonable way of seeing the universe, we think of it as having 3 spatial dimensions. And not only our universe, the real one, has 3 dimensions. When we're making games, we're making fake universes. We're creating stories and fictitious things, but I'm thinking about fictitious universes that are also 3-dimensional. So unless you're thinking of like some Discworld kind of thing, your game probably, like in your mind, your imagination, the world of your game is 3D, right? So that's like one end of the spectrum. Like you have this in your mind, this game has 3D. But in the very other end, we're showing that game in a monitor, right? And the monitor is 2D. well, the monitor object is 3D, exists in the world, but we're showing the game in the screen of the monitor, and the screen is a grid of pixels that's 2 dimensions. So what happened? Like, all the way here got 3D, and all the way here got 2D. So in between, something happened. Some transformation happened that allows us to change from 3D to 2D. Now, I'll also mention this once that maybe your game is not shown on a screen, so there are other possible ways you could make a game, right? You could have like a VR game or some 3D goggles kind of thing, like those movies, or maybe you have a hologram, like, sure. We're not talking about those kinds of games. We're not talking about games that are like 2D in your imagination. We're talking about things like when you think about like Link walking around with a sword, right? In your imagination, that's a 3D world, and we're talking about showing that 3D world in a 2D screen. So there is some transformation here. There's this process that we're going to define. So we're talking about 3D rendering, but let's break it down a little bit more, because I said, sure, in our imagination, the world is 3D, right? But I still want to break it down into 2 parts. So maybe in our imagination it's 3D, but in the actual code, your game is 2D. So what I mean by that is you have maybe a player class, or you have enemy, and they have X and Y. They have 2 coordinates. So you're thinking of your top-down games or your platformer games, right? So in that case, the conversion happens in your mind, because the game is actually 2D and it's rendered in a 2D screen. You're imagining this 3D stuff in your brain. And that's the whole point of the previous talk, where I gave several techniques to make your game look and feel like 3D, even though it's a 2D world. But we're focusing on the second one today, where in your code, the game is already 3D. So you have your player class, and it has a 3D positioning space. It has X, Y, and Z. And somehow we were locked on the screen, right? We need to get to 2D. So specifically this arrow here is kind of what we care about, what we want to understand, how this transformation happens. So instead of having a player which has like a vector 2 position, let's say, with X and Y in 2D space, we actually have 3D space, and we have a player with vector 3, right? So this is going to be what we're talking about. And then, well, I don't know how this transformation happens yet. We're going to see. So we're talking about 3D worlds rendering. Not only that, I'll make it even more specific, because there are 2 ways we can do this 3D world rendering. So basically, we have that arrow, right? We need to convert 3D to 2D somehow. So we can do that 2 ways. We can do that in the CPU, or we can do that in the GPU. Now, in the CPU, I also already showed that on the previous one. That's not how any modern games are made, but it is possible to do that. So basically, when you run your Dart code, or most code you write, that code is being run on the CPU. And you can do anything on the CPU. It's a general purpose thing. So you can do all the graphics transformations that we need on the CPU. So last time I showed this sample, which is just a playground that I made using fully CPU-based rendering. Now this ran totally fine. Probably if you added a few more low poly objects, that'll be fine. But it won't scale, right? It's not the real 3D that we're talking about. So the real 3D that we're talking about is using the GPU. So what's the difference, you might ask? So as I said, the CPU is a general purpose thing that can compute anything. And when we're talking compute here, it's multiplications. We're doing lots of multiplications. So if you want to make a few multiplications, the CPU is going to do it in sequence, one after the other. And it's actually super fast. It is faster than the GPU if you want to make a single multiplication. But if you want to multiply the same numbers again and again in different shapes, which is basically what we're going to be doing, I'm going to show, I'll give you a hint right now, it's all about matrices and multiply matrices. That's what we're going to see. If you want to do that, well, people came up with this other type of processor, the GPU, which is really good at multiplying multiple numbers, same numbers, multiple times. So we want to leverage the power of this GPU. But as I said, the normal code you write, your Dart code, your Flutter, your Flame code, is mostly running on the CPU. You're giving instructions to be run on the CPU. So how can we access the GPU? That's where the new Flutter GPU package comes in. But in general, in order to access the GPU, you need a separate thing. So you could think of it as a set of tools or framework or language. You can call it any of those things, but basically there are different mechanisms we can use to access the GPU. Now the most famous ones are called OpenGL or Vulkan, which is kind of an upgraded, newer version of OpenGL, but most things use OpenGL, which is like in the open source version. You can think of it as a framework to access the GPU. Now this is kind of platform dependent because you might also have heard of Metal on the Apple stuff, and you might have heard of DirectX on Microsoft. Those are the same things. Their APIs allow you to access the GPU, but we don't need to care about that because we're talking about Flutter, right? And Flutter is cross-platform. So ideally, we have this Flutter GPU package that kind of delegates to whatever underlying platform. But if you want to write, GPU code from scratch, if it's related to graphics, you would use OpenGL and those kind of things. Now, in general, I'm just going to say OpenGL. Doesn't matter which actual underlying implementation is being used. It's just a shortcut. So when I say OpenGL, it's basically the underlying code that allows games. So basically, any recent modern game, like even if it's 2D, it's probably using some OpenGL equivalent to render stuff using 3D and the CPU and the GPU. Now, originally the GPU was intended for graphics, but what it's good at, as I said, is multiplying lots of matrices, lots of numbers, right? So some people realize that they might want to use that power to do other things. And then there are some other languages that you can use if you want to do, let's say, general purpose computing in the GPU, leverage that power, but it's not graphics. There is some open source versions, but sadly the most famous one that you might have heard of is the NVIDIA CUDA, which has been very famous recently because there's been this new fad that people love and have been all overhyped about. This new fad that people love, that's been overhyped about, that people use the GPU for. But we're not talking about that, we're talking about graphics. So we want to render those 3D worlds, but we want it to be GPU accelerated. And more important, one more thing, we want it to be first class. So before, we could probably think of ways to hook this up with Flutter, with some native channels, method channels, platform stuff. But we wouldn't want to do those kind of hacks, right? With the power of the Flutter GPU packages that Brandon bestowed upon us, we can now have a first-class GPU accelerated 3D world rendering. So this is our problem. So when you say 3D, that's shortcut for all that. And can we do it? Can we do 3D? Yes, we can now do 3D. Well, some asterisks. Yeah, well, kind of. So yes, we can. But as with Flame in general, this will not be your very mature, established, there are other game engines there if you want something like Unreal to make like a full AAA games. But if you want to make something simpler and you're willing to go along with us and maybe find some bugs and maybe help along the way, you can. In fact, some of the, let's say, unpolished state will show up by the fact that you're going to have to, first of all, use the Flame 3D package, but that's not even in the main branch of Flame because this requires the Flutter main branch, and Flame depends on stable. So you're going to have to use the Flame 3D branch. Now, I published these packages on Pub, so you can use it over there. I also created this Flame 3D extras package with more things that I haven't had time to merge into the main Flame 3D yet, but eventually it should all be one package. I do recommend, if you're going to do it, to use the dependencies override and basically clone those two repos from GitHub, and then you can kind of get the latest version, and if you need to make any changes, you're like very easy to do. Another sad thing is that it will not work on Linux. That's because the Flutter GPU, as I said, even though it's intended to be a cross-platform, unifying kind of API that will basically delegate to the underlying systems, it's also still very experimental, and they have only released it for Mac OS. Hence, I have to use this. I tried to disguise it, hide it a little bit, but yeah, it's a Mac. Sadly, it's not going to work for other platforms yet. But I believe Breno is working hard on it, so I can't wait to see it run problems. So if you're willing to put up all this, this is kind of a diagram of what it can look like. So you're gonna have your game code, right? The code you're gonna write for a game. And that code will use the Flame library and the Flame 3D package. So ideally, you won't need to interact with Flutter GPU directly. Flutter GPU is a much lower level API. I'm gonna show what Flame 3D is doing for you, but hopefully you won't need to muck it with too much. You might need to touch it a little bit. Again, if you find some missing feature or some bug or something that should be a little bit different. And then Flutter GPU itself will talk with the underlying APIs to accessing the bare metal, so that will be OpenGL, or, in fact, it will be metal because it's only for macOS right now, but in general, it would be some OpenGL version. And then that access the actual bare metal, the GPU, which renders the 3D stuff. And similarly, you have, just plain old Flutter here, which uses the CPU. So if you have, menus and stuff in your game, you can use Flutter as usual. That doesn't change. Okay, so this is our ideal flow that we're gonna do. So let's talk about the Flame 3D and how to use that. And more specifically, let's talk about 3D rendering as a whole and how does that work. It's a little bit different than the concepts that we know from normal Flame 2D. And let's start with a secret. So just a recap, we're converting something from this 3D coordinates. So we have vertices or points that are in this 3D space, and we want to convert that into a 2D space, which is our screen, which is the X and Y. We're actually first going to arrange those into triangles. And the reason for that is a triangle is the simplest shape that you can have in 3D. That's like a surface, right? And you're going to see the GPU is going to be really good at drawing any triangles. Now, any polygon you can break down into triangles very easily. You can just draw the lines in between. So basically, we're going to assume everything is a triangle. If you want to render round shapes, you're also going to have to approximate those with triangles. And basically, the amount of triangles you want to use, the better the approximation will be, but the more expensive computations are going to be. As you can imagine, no computer, no CPU, GPU, no one likes round things, right? They like straight lines. So that's why I approximate for triangles. So we compose 3 points into this 3D triangle that lives in 3D space somewhere, right? Well, we're actually going to render a 2D version of that triangle, which has been translated through a camera to fit on your screen. So this middle arrow here is kind of where our transformation is going to be. So that transformation I'm talking about is this arrow. And that's going to be a piece of code, actually, right? We need some code to transform. But we want to run that code on the GPU, so we're going to get that. But what's the piece of code here? I gave you a hint before. I mentioned matrices. And actually, everything you're going to do, everything you're going to talk about with 3D rendering is all multiplying matrices. It always has been multiplying matrices all along. Now, as I said, hopefully you won't need to. I know matrices can seem scary for some. You won't need to go into too much detail into the matrices, but we need to kind of know what they represent at least. So this is the only slide I'm going to show, the matrices, so don't get scared, don't go away. This is really quick. Basically, what a matrix represents is a transformation for a point in 3D space. So you have a point or a vector, 3, right, somewhere in space, and maybe we want to translate it, right? Or maybe we want to rotate it, or maybe we want to scale. So those transformations, each one of them could be represented by, say, a vector 3 for the displacement that you want to translate, right? But all of them combined, you can represent by a single 4x4 matrix. These 4x4 matrices are affine transformations in 3D, and they are basically the essence of everything we're doing. We're translating things from one space to the other. Sorry, we're transforming things from one space to the other. That could be translation, rotation, or scale. And the key thing to know about the matrices, this is very important, is if you have 2 of them representing 2 different transformations, and you want to apply both, you can just multiply those matrices first, And if you multiply these two 4x4 matrices, you get another 4x4 matrix that you can then apply to your vector. So that's what makes this so powerful, because you can do any amount of transformations you want, and you're always getting back the same type of thing, the same matrix 4, right? So you can write very generic code that just takes a matrix 4, and it could take in anything, basically. But as I said, we don't need to go too deep into the matrices, because if you want to know more about this, you can watch my previous talk that was all about how to do this in the CPU, and I went into more detail. But this time, the GPU is going to do it all for us, because it's a good guy. Now, it's a little bit more involved, so how do we tell the GPU what to do? A lot of things are built in, and we don't even need to worry about it, but we do have to write some code. Now, I've been saying that your Dart code runs in the CPU, right? So what kind of code do we write that runs on the GPU? Well, they're basically called shaders, which you might have heard in other contexts, because you can use them to do cool 2D animations as well. If you watch Henan's talk about shaders, he has like dozens of amazing examples that look way better than anything that I can do, but those are mostly 2D. Now, we're going to use shaders to basically do all those matrix multiplications that we want. I'm not going to explain shaders because, again, this is already kind of bundled into the Flame 3D package. So if you are using Flame 3D, I'm hoping that you don't need to write any shaders. You don't need to know any contents of any matrices. You might need to pass around some matrices. If you want to like rotate things, you might need to create a rotation matrix. But that's not necessarily true, because you might need to tweak this if there's some special thing you want to do that we don't currently support. In that case, I leave a resource link if you want to know more about how shaders work. This is the best one I've seen that really taught me a lot, especially about lighting. But just so you get a sense of it, what really is important here is that it's a language. It's very C-like, but it's not exactly C. And it has this global inputs and outputs. That's basically part of the rendering pipeline. So what's going to happen is we're going to send the 3D coordinates, basically, to the GPU and tell the GPU, hey, render this. And then the GPU is going to do some stuff, and then it's going to call our first shader, which is the vertex shader, and it's going to take in those positions, and the vertex shader, sorry, the vertex shader will tell the GPU how to project those coordinates into the screen space, which is all these multiplications you see here. By the way, this is a simplified version of our vertex shader, so that's why I don't want to get too much into it. And then you'll go into the fragment shader. That one will determine the colors, or what it will look like, which will be affected by things like lighting, right? So basically, what you need to know is we're sending some data to the GPU. The shaders will compute on top of it, and the output will be this 2D image that will be rendered to the screen. But what are we sending to the GPU, right? I said we're sending the positions, the coordinates, or the vertices. So if we think back to our triangle, we have 3 vertices, right? So we just send the 3D coordinates of those vertices. Well, not exactly. We need to send a little bit more information. So within each vertex, each point, we're going to send a set of information to the GPU. This is all sent as bytes, so it's a little bit hard to do. Hopefully, I have implemented it in a way that you just create your vertex and it does it for you, so you don't need to worry about, byte offsets and paddings and all that kind of stuff. But again, you might encounter some issues, so that's why I'm telling you ahead of time. So what are we sending? We're definitely sending the position. That's the 3 coordinates of the point. We also need to send color or texture information. We need to send normal information and joint information. So let's go over a little bit real quick. Now, one thing to demystify here, these vertices, they're not pixels. We're not going to send every single pixel that we want to fill in. That's the job of the GPU to do, to figure out which pixel level. We're just saying we want a triangle, and these are the 3 vertices of the triangle. So you might think each triangle has 1 color, right? And normally, yes, you are either using a texture or your triangles have a single color, which means all your 3 vertices have the same color. Now, it does allow you to send different colors. If you do that, it will linearly interpolate the colors, and you get some gradient like this. I don't think that's really common within 3D games, but if you want to make something fancy, you can use that. But in fact, not even flat colors are that common because probably you're gonna want to use a texture. So a different way to fill in this triangle is to use an image. A texture is basically just a 2D image that we're gonna stamp and mold into this triangle. And the way we deform it to fit the shape of the triangle is specified by these coordinates. So we're using U and V as the name of the coordinates here, which is basically a normalized. So you can think this is X and Y for the image, but it goes from 0 to 1. So it doesn't matter if you, if you change the texture size, it's not gonna matter because you're using like these normalized coordinates. And we're basically telling for each vertex what part of the texture we're gonna stamp on that vertex. And then the GPU is gonna distort the image to conform to a triangle. So for example, if you're drawing a box, this is what the texture might look like. But if you're drawing a square, you know you need 2 triangles, right? So you're gonna map accordingly these textures accordingly to the triangles that you wanna render. Then we need normals. So normals is the perpendicular line to a surface. You might be asking, why the hell do we need that? We just wanna render the triangle, right? Well, we actually don't really need that, but we're gonna see later about lighting and how we can have moving light points and custom lighting stuff. In order to do lighting, the underlying physics formulas that we're gonna use require us to know the normal to each surface. Now, again, we're sending stuff per vertex, right? So each vertex will have its own normal. The simple case, I'm gonna show some other cases later, but the simple case is we just calculate the surface to the normal to the surface, and we send the same normal 3 times on all 3 vertices. Now, this has some drawbacks that I'm going to show later, but this is like the intuitive way of thinking about the normals. Finally, we have the joints information. Now, this is a little bit more advanced. This is when you are using skeletal animation, which is basically a much cheaper way of doing animations, where instead of, think of your complete mesh, where you have hundreds of vertices, right? And you want to animate that, you would need the animation path of each single point of all your vertices. That could be thousands, maybe even millions of points for each. You have independent animation transformations. Instead, the clever way of doing it is you have your mesh here, and then you have a separate structure, which is your skeleton, which has very few nodes, maybe like 10 nodes. And that's the base of your movement. Then we animate the skeleton, and for each vertex, it just says how much tied up to each bone in the skeleton it is. And that's just some more efficient way of doing animation. And it has many advantages, but I'm not gonna go into too much details, just so you know, this is part of the stuff that goes into each vertex. So here's the class, as seen in Flame 3D. Position, the texture, coordinates, color. Now note that the texture itself is not here, because that's huge, right? We don't wanna repeat that for each vertex, so we're gonna put that a layer up in the hierarchy. But everything here can be configured per vertex. So the color, for example, is very small, it's just 4 numbers. So we put it per vertex in case you want to do the linear interpolation thing. The important thing about the vertex here is that everything we're passing here, we're all gonna jumble that into this list of bytes, this byte buffer, and that goes into the storage. And that's what we're sending to the GPU. But we're not gonna send one vertex at a time. That'll be too many trips, too inefficient, right? So what we actually want to do is to create a surface. So if you think of a 3D surface that's not a triangle, it's made out of triangles, right? So if you want to render a square, you're going to have 2 triangles, and it's going to form a square. If you want to render like a complex polygon shape, as long as it's a surface, you can divide that into triangles, and we're actually going to send all those surfaces at the same time to the GPU. And one of the reasons to do that is because if you think about it, a lot of the vertices are actually shared across multiple surfaces, across multiple triangles within your surface. And the way we do that is we send the list of unique vertices, and then we send a list of the indices, the IDs of these vertices on the first list in order to define. So for example, in this case, we would only send 4 vertices, but it actually needs 6 vertices, right? So we would define the 4 unique vertices and then use their IDs to build the actual list of vertices. So again, some optimization to make it so we're sending less data to the GPU. Again, we're doing this every frame. So every once 1/50, we're doing this. So we're trying to optimize. This is also where we send the material. Now this is a fancy wrapper, but basically this has the texture. So if you're using the texture, all the bytes of that image are going here. And we also need some more joint information related to the skeletal animation. We also have these calculate normals here because if you just define the surfaces with no normals, there are algorithms that allow you to compute where the normals are. We want to run this once when you create a surface and not every frame. But you might also want to specify your own normals because there are a few different ways of doing it, which you might want to do like a custom way. So this is a surface. So this would be like a square or a polygon or a hexagon, whatever you want. But we don't want to draw surfaces. We want to draw a full 3D solid, right? So that's what we call mesh. So a mesh is a single 3D shape that's composed of many surfaces. So for example, if it was a cube, we'd have 6 surfaces. It's just a list of surfaces. And importantly, for meshes, we define this AABB. This is a term you're probably going to see a lot if you're working with Flame 3D or just 3D in general. That just means axis-aligned bounding box. It's basically the smallest rectangular trapezoid, let's say, or like cuboid, that completely contains your whole shape, but it's the smallest as possible. So it's your bounding box, basically. And this is used for a few things. In particular, for the rendering, it can be used for culling. Culling is when we determine that things are completely outside of the camera and don't need to be rendered at all, so we just skip those. In order to do those computations, we don't want to inspect the complex geometry of all the vertices and shapes of your thing. We just want to do a first pass using this simplified underlying shape. Now, in the case of the cube, the bounding box is the cube itself, but obviously you're going to have more complex shapes than cubes. The AABB is also used for collision detection. Now, there's not yet any physics built into Flame 3D, but you can do very simple physics using the AABBs and doing just simple intersection detection. I'm going to show some examples later. Okay, so we got the mesh. Now, as I said, the simplest mesh we can do is a cube. So let's do a cube, right? Now, in order, if you remember from the video I showed the cube, you can see a cube is actually made of 6 surfaces. Each one has 2 triangles. So that's 12 triangles times 3. That's 36 points you need to define just to draw a single cube. You can see here the code. This is just part of the code. That's just 1.5 faces. So you can see this guy wild, right? Now, if you want to draw a simple cube, of course I already coded that, and it's called cuboid mesh. And you can just use that, obviously, so you don't need to define the points one by one. You just say the size of your cube, your cuboid. So, by the way, cuboid is just a cube that has different sizes for each length. I don't know if there's a better word in English for this objects, but you can think of a cube as a special case of the cuboid where they're all the same size. So if you want to draw any sort of rectangular cuboid, you just provide the size of each. Here, I'm making an actual cube, so 8 each size. And yeah, you can draw it. Now, you obviously don't want to specify the vertices for all your shapes, right? For like a very complex shape. So we're gonna have ways around this. We're gonna use models instead. But this is underlying, like all the meshes are eventually just lists of vertices. Now let's talk about a little bit about lighting. So I mentioned we have those normals and we need those for lighting. So very important to note is that in Flame 3D, you're gonna have to add some light, at least one. Otherwise, everything's gonna be black, and you're gonna think it's not working. It's because you didn't add the lights. Now, there are many types of lights you can have. There's some already open in issue in Flame, asking for us to provide other types of lights. But the ones I implemented so far is only these 2. So ambient light just lights everything the same. It's not position dependent. This is like what you think of lighting. If you think your game doesn't have lighting, it just has ambient light. So you can just add that. It has a color. If you make it white, that's just normal, like all colors lights, which will reflect the true color of things. If you make it tinted light, it will have, the expected interactions. And it has intensity. Alternatively, you can make a point light, which is one point that emits lights in all directions. You can use that to make like a torch or a lamp in your game, or if you want, you can even have it to move, which I'll show in a little bit. I have here the component hierarchy structure. So for example, we have component 3D, that's the basis for everything. It can be an object, which is something that's rendered, or it can be a light. The lights themselves are not rendered, they just change how the other objects are rendered. So that's why they're separate things. So the light can be ambient or point, as I said, and the objects, you're probably not going to use this. You're going to use the mesh component directly because you're rendering a solid. Or if you're loading from a file, you're going to use the model components, which we're going to show in a bit. The underlying physics of the lighting is a little bit complex, so I'm not going to go into detail. There will be some links at the end as well if you want to explore more about how these things are derived. But basically, you just provide the normals and the positions and intensities of the lights, and the shader does everything. Now, this is a little bit limited so far. For example, I couldn't get dynamic arrays to work, so you're going to be restrained to the number of lights that I hard-coded, which is 3, but you can have more. You just need to change the flame code. It's very easy. Just a lot of copy and paste, which I hate, but sadly, it is what it is. So far, I'm really trying to get the dynamic arrays to work, and then that will be no issue. We don't have other types of lights. We also don't support shadows. Again, this is very bare bones, and we're kind of counting on you guys if you're interested and excited about this to help out as well. This is explaining different types of normals have different effects. I'm just going to skip this in interest of time. Yeah, I have a little demo here about lights. You can see there's a moving green light. It's not very obvious, a little bit subtle, but the moving green light is here. This is a static light. Anyway, I have better videos later. So we don't want to define the vertices of every single thing by hand. So what do? Well, we load a predefined model file like this. So you go to the internet, you can find models for everything. This is the classic teapot that we showed on the previous video. Now these models are files, and there are different types of files that we can use to describe this. Now I had to make a choice here of which files to support. I picked these two. So the OBJ file is the simplest possible one. It's just define a geometry. And then the GOTF is the golden standard for this kind of file. It's open source, and it contains all kinds of possible information that you can think of. As I said, the OBJ file is very simple. It's just a list of vertices and a list of normals. And with that, I had made before this game called Defend the Donuts, which is kind of a space team thing. I'm going to skip a little bit ahead. You can look around. There's a donut. You're like this ship, and you find other ships, and you fight them. There's another ship. You can shoot. That's kind of your basic 3D space shooter game. But I wanted more, so I wanted to implement a GLTF type file. Now this has a lot of more advanced things. It's no longer a plain text file. It has JSON, but it also has bytes inside the file. It's very complicated, but this is the kind of file you're going to find easily online. And the parser that I implemented will convert that into this class called model, which is just a representation of that. The reason it's not a mesh is because it actually has multiple meshes in a tree structure called nodes. And that's because of how the animations interact. So you want to have an animation that affects a subset of the tree structure. So we need to preserve that tree structure into the model class. So you can think of it as something above the mesh, as a set of meshes. And how you use it is quite simple. You can use this model parser. Then you can parse GOB, GLTF, OBJ files, anything into this model class, and you provide that to the model component, which allows you to position it, scale, transform all those matrices that I showed. And it allows you to play animations. So the file itself, the model itself comes with its own animations, so you don't need to do that. Now, you're going to have to do some other stuff like moving the model around. That's up to you. But animating comes within the file. And okay, that sounds good, but can we get an actual game out of this? Well, yes. So I'm not very creative. So I took the inspiration of Defend the Donut. I just made Collect the Donuts. I wanted to show here, this is the entire code base of the game. So I think it's not that hard to put this together. It's a little bit of files, but if you think about it, it's very similar to the amount of files if you had a 2D game, right? You're gonna have a floor component, player component, skeleton component. Well, we have skeletons, I'll show that. That has some menus code, and then just the main files, some loader stuff, some utils. You can go to the repo right now to see, but we can see a short video. So this is 3D within Flame with lights. The lights don't do anything, just to show the lighting engine. But you can walk, you can run. And again, this is all models that I picked up online. If you go to h.io or some other websites, you can get really cheap or even free models. And you can walk around, you can kill the skeletons, and most important, you can collect the donuts. That's your high score there. Yeah, and you can also attack. You can also die if you don't attack. It's very simple, but you know, that's just providing the tools. I hope you guys have the actual inspiration to make an actual cool game and not something nonsensical like this. And yeah. So I think I'm running out of time. So I'll just say what to expect. It's not gonna be super polished, it's not gonna be super mature. So this is not like production ready. A lot of things that I listed here we don't have. I cannot even make a race. So look at this nonsense that I had to do. Yeah, I'm very creative. I can make a raise without a raise if I need to. But yeah, so I still work on that, but the main call out is if you're interested, if you're down to the challenge, if you're willing to accept the caveats that I mentioned, and you want to help, and you want to make some cool games, simple, low poly probably 3D games, and contribute to Flame at the same time, that's my ask for you. And yeah, I think, are we out of time? Do we have time for questions? Do we have time for questions? Or yeah, any questions? So each square here, I got this back on itch.io. K-Kits, it's called. I love it. So cute. So this floor tile is a model. If you look at the floor components, it will do the tiling for you. So it's basically creating like, however many, you say the size of your floor and it will create how many, whatever you need. Same for the wall. So each section of the wall here is one model. And the code there will randomly generate a strip of wall, the length you want. The rogue character, which is this little dude, it's a model. It has all the animations. It has walking, jumping, shooting, anything you want. The skeleton is another model. The donut is a model. Yeah. The only thing that's not a model here is the lights. The lights I made, so they're normal lights, but if you see, I also rendered a little sphere, whatever the light is, of the color of the lights. So it looks like, I call them wisps. It looks like a firefly. Obviously you can do different, like, the light itself doesn't render anything. It just changes how other things are rendered. But I created the sphere there just so you know where it is. Yes?
So did you say for the floor tiles, those are programmatically replicated instead of just individual?
Yeah, the code is really simple. If you want to look at the repo, it's the floor.dart file. You see it's just a for loop. Very simple stuff. Okay. Yes. I'm not familiar, but I know there's a talk tomorrow about it, so definitely check that out. I don't know how much Flutter is integrated with it. I know the talk tomorrow is on the droidcon side, so. Okay, I think that's all I have time for, right? Yeah, because otherwise I'll keep going forever. Thank you.